we'll move to some aspects that have actually already appeared just a few moments ago, since he was mentioning subordination functions. And I want to discuss that particular topic, which allows one to go a little bit more closely into the analysis of free convolution. So that for large for the law of large numbers and for the central limit theorem, for instance, it was enough to consider the behavior of R transforms of functions at infinity, so to speak. Okay, but when you want specific information about measures that you're obtaining when you do free convolutions, you really want to get close to the real line. So that's how does one get to that? And well, I'll start with a few things from complex analysis, which perhaps are not universally known. And I wish I had known them a little earlier myself. So maybe this will be useful for some of you. So my notation here is for D is the unit disk in the complex plane, H is the upper half plane. I used that notation before. They are basically the same domain. They are identified by this conformal equivalence that maps Z to the fractional linear transformation Z minus I divided by Z plus I. And we will often switch between the two of them. The essential difference between these two things is that the upper half plane is like the disk, but one of the points in the boundary of the disk has been thrown out of focus, so to speak, or perhaps is put into focus, the point at infinity. Functions that are analytic self maps of the upper half plane can be written explicitly using this formula. So phi of Z is alpha, a real constant, plus beta times Z, plus an integral of kind of a Poisson kernel, 1 plus ZT over T minus Z, d rho of T. Notice that it's T minus Z today, not Z minus T. Or if you want asymptotically, as you go to infinity, this is beta Z plus something which is little o relative to Z. Non-tangentially, I should say. And the truth is that the constant beta and the rho, the two of them together should be considered as a single object. It's really a measure defined on the extended real line. You just add the point at infinity. So beta is the mass of the point at infinity. Right, so if you notice that if you take that integrand and you let T go to infinity, that what you're going to get in the limit is Z. So that's basically the integral extended to the whole real line plus the point at infinity. But it's useful to single out that point at infinity. The way that you prove this particular formula is via the Herglotz representation of functions with positive real part in the disk. So it's a very classical result, and this is called the Nevalina formula, right? Did I say Nevalina? Maybe I didn't, but I wrote it. Attractive. Sorry about that. So it's the third time that I make this mistake. I think it appears one more time here. Yes, if phi is not the identity function, if beta is greater than or equal to 1, then infinity is kind of a fixed point for the function, an attracting fixed point, not attractive. Maybe it's attractive also, but I'm sorry. It's attractive, yeah, man. That's more of an aesthetical statement. Yes, so it's an attracting fixed point in the sense that the iterates of the function go to infinity, right? So so you just move up higher and higher to the upper half plane, except of course when the beta is equal to 1, you go to infinity a different way, right? Okay, so that's an attractive thing. I think I'll never learn this. Okay, so first there is a result of Julia and Cartier. I'm not going to state the exact result the way that they had it, but it's well, perhaps I want to say something a little more general than they had it, but it serves my purposes for today. And suppose that you have some positive numbers yn and yn prime that go to plus infinity, and yn prime is greater than or equal to yn. And you have these functions phi n analytic from the half plane to itself that map iyn into iy prime n, right? So they push some points up on the y-axis. And you also know that phi n converges to phi pointwise. All right. And let's say that phi n is represented using the Nevanlina representation using parameters alpha, beta, rho, and alpha n, beta n, rho n as the Nevanlina formula. And there's a theorem, which is essentially the Julia-Cartier theorem, that beta is greater than or equal to 1 in this case. A little bit more general, but this is and I'm going to inflict on you proof. Since the third lecture, there have to be at least 3. Actually, there will be 4 proofs, and therefore tomorrow there will be 0. Right, it's a special sequence. 1, 2, 4. Okay. The convergence of the functions phi n to the function phi is equivalent basically to saying that the whole measure rho n times point, so point mass beta n at infinity plus the measure rho n converges to the corresponding measure beta mass at infinity plus rho in the weak sense. Finite measures, and they converge in the weak sense on the extended real line. And now we will compare imaginary parts. So comparing imaginary parts, you get this inequality. One is less than or equal to yn prime over yn, but the yn prime is exactly the imaginary part of phi n of iyn, right? So you calculate imaginary parts, you get that yn prime over yn is beta n plus the integral of 1 plus t squared over yn squared plus t squared times d rho n of t, which you can majorize by, maybe I should get closer to the screen here. Yeah, you majorize in this particular fashion. You look at the mass rho n in a certain interval from minus t to t, and the mass outside the interval minus t to t, where we majorize the integrand simply by 1. T squared over yn squared plus t squared tends to 0 as n goes to infinity in every finite interval, and even uniformly on a finite interval. And outside, it's less than or equal to 1. So what conclusion do we draw from here? We draw the conclusion that beta plus rho of the complement of the interval from minus tt has to be bigger than or equal to 1 because the middle term goes to 0. Right, so this term right here disappears, and beta n plus that converges to the corresponding expression without n, at least for most values of t. So beta plus that measure, the measure of the complement of n from minus t to t is at least 1, but of course you can now let t go to infinity and get that beta itself is bigger than or equal to 1. It's a nice little observation. Okay. Now a word about the Julia-Cartier derivative. So suppose that you have a function phi from the upper half plane to itself, which is written in that particular format. Beta is strictly positive. Actually, you don't even need to assume that beta is strictly positive, but beta could be 0 also. 1 over beta then is called the Julia-Carré-Theodori derivative of phi at infinity. So it's an exercise for you here. Why is it beta? Why is it 1 over beta and not beta? Okay, homework. Because after all, that's the linear term, and that's something that's smaller than the linear. But anyway, 1 over beta is the Julia-Carré-Theodori derivative of phi at infinity. What? Don't. That's something to be done privately. Yes, and yes, of course. And now as you say, the upper half plane is conformally equivalent to the disk, and this is basically, you can say that this corresponds. Infinity corresponds to the point 1, but the disk is kind of nice and symmetric. You should be able to talk about the Carré-Theodori derivatives at other points rather than infinity. So let me translate this to other real points. So, so for other fixed points on the real line, fixed type, you should notice that I put fixed in quotation marks because this is not really a fixed point because the function phi is not defined on the real line. But it's fixed in the sense that the vertical limit at a particular point, phi of t plus iy tends to t as y equals to 0. Okay. Then the Julia-Carré derivative at the point phi is one of these 3 equal quantities. One of them is the limit of phi prime of t plus iy as y goes to 0. That's closest to what you think is a derivative. The second one is the lower limit of the imaginary phi of z over the imaginary part of z as z tends to t. Notice that in this limit there is no limitation on how you converge to the point t. Okay, lim the smallest possible value that you can get for sequence zn converging to the point t, and it's also an angular limit, which here looks a little bit more like a derivative again, right? Phi of z minus t over z minus t, as z tends to t, but here it has to tend non-tangentially to the point t. It's modified. You have to conformally transform it at infinity. But it is basically true. But you notice that at infinity, if you calculate phi prime, or formally at least, if you calculate phi prime of z, you get beta plus something, and as z goes to infinity, the limit seems to be beta, the limit of the derivative. So that's why it's a little bit of a conundrum as to why it should be 1 over beta, but why the derivative should be 1 over beta. But it is. That's the correct. Yes. Function phi from the such a function phi might have many such fixed points on the real line, but the Julia-Carré derivative will be generally bigger than 1, perhaps even infinite. All but at most 1 of these points. And I think you see right away why that is the case. Is the fact is that that point where the derivative is less than or equal to 1 is an attractive. It's an attractive fixed point. The iterates converge to that point. They cannot converge to 2 points. Yeah. So there'll be at most 1 point where the derivative is less than or equal.
You already have one at infinity.
No, I'm all for equal rights and everything, but in this case, there's just 1.
Okay, but you say, well, there cannot be more than 1. Seems like a false statement. You could have many interacting fixed points at different points. They each have their own basis of attraction.
No, because it's for every z. Wherever you start, wherever you start, and you apply the iterates, you converge to that point.
Okay.
Yeah. I mean, just let's go back for that. Let's go back a little bit. the formula. Just look at the formula. Beta is bigger than, if beta is bigger than or equal to 1, just iterate this formula. Alpha plus beta is z plus that. Let's say that beta is strictly bigger than 1 for the moment. Then you take an arbitrary point z, it has, say, imaginary part equal to 5. You apply phi of z, you get an imaginary part which is greater than 5 beta. You apply it one more time, you get 5 beta, get 5 beta cubed. Just goes off to infinity. Have another point like that. So yeah, this is a situation in which the Giulia-Cara-Teodori derivative I don't hear discriminates. Sorry, I don't like to do this kind of thing, but it's and now we come to two other gentlemen from the same historical period, as far as mathematical contributions are concerned, which is about 100 years ago, maybe 90. So Danjean and Wolf consider the function psi, which is analytic from the disk to itself now, rather than the upper half plane. It's analytic and it has no fixed points, no true fixed points. It doesn't fix any point inside the unit. And here's the theorem. It's missing a hypothesis, unfortunately, but this function psi should not be the identity function. Yeah. Oh no, actually, it could be the identity function. Just the identity function doesn't satisfy the hypothesis. So it's have an arbitrary analytic function. It has no fixed points. Then there exists such a point in the boundary such that the iterates of the function converge to that point for every z. So in other words, if you don't have any fixed point inside the disk, there is in fact that point on the boundary where the Giulia-Cara-Teodori derivative is less than or equal to 1, which is therefore an attractive fixed point with quotation marks. Okay. So how do they prove this? Well, suppose that R is between 0 and 1. Actually, it would be better if it would be an open interval, if you don't mind. And denote by psi. Yeah, if you look at the map that takes z to psi of R times z, that's a map which is analytic not only on the open unit disk, but it's continuous on a bigger set. It's analytic even on a bigger set, and therefore it has a fixed point. By whatever you like, apply. Brouwer. Yeah, let's appeal to Brouwer. Brouwer fixed point theory tells you that that function has a fixed point. So there's a ZR such that psi of RZ, R times ZR is equal to ZR. ZR necessarily have to converge to 1 in absolute value. You see why? And there'll be a subsequence of them which converges to a point inside the unit disk, which will be fixed. So bad news. That's not allowed. So ZR has to converge to 1. And choose some sequence Rn that converges to 1, such that Zn is Zn, which is Zrn, converges to a point zeta in the boundary of the unit disk. Right? So there must be an accumulation point anyway, but it's on the boundary. Okay. Now rotate psi a little bit, and write psi of z as zeta n psi of Rn zeta over zeta n, such that Psi converges to Psi, and Psi of Rn absolute value of zeta n is equal to absolute value of zeta n. Well, this is assuming that zeta is equal to 1, just to simplify matters. Yeah. So it just, yes.
Zeta n.
Zeta n is some number of absolute value 1.
But the argument of CRN.
You just change the argument a little bit, okay? So you take the function, you rotate it.
Yes, the argument is Z sub RN.
No. It's some number. You just choose it. You just choose it wisely, okay?
That's about it. Depends on this.
But this is something to have. You know, we cannot do quite complete proofs here, right? But it's pretty complete. This is pretty complete. So just choose it. So suppose that function zeta is equal, that point zeta is equal to 1. So this will tell you that the arguments of the zeta of the z's converge to 0, right? So e to that argument will converge to 1, as you say. Yeah, so you can take that to be the argument. And so this has the advantage that Cn of Rn times the absolute value of zeta n is equal of Zn is equal to the absolute value of Zn. So they are on the same radius, you see. That's the, I just moved them a little bit to be on the same radius. Thanks for the completeness. All right. And now trade the disk for the half plane. What happens when you trade the disk for the half plane? What happens is that the radius, the segment 0, 1 in the disk corresponds to the imaginary axis in the half plane. So you have now this functions Cn, which converge to Psi pointwise, and they move some points on the imaginary axis. They move them a little bit higher up, right? So you are exactly in the situation of the Julia-Carré-Theodori, of the Julia-Carré-Theodori theorem. So once you change your point of view, and you move to the upper half plane, you place yourself under the hypothesis of Julia and Carré-Theodori. End of proof. Beta is bigger than 1. Infinity is an attracting the fixed point. Yeah, further questions about this little argument? It's very simple. I mean, it's not. But it is simple because I reorganized a little bit Julia and Carré-Theodori to make it simpler, to make it simple. And as I was pointing out a little earlier, the zeta is of course unique because it's an.
Why isn't there never been a representation of functions from the disk to itself? You just use the beta for that, rather than going to the upper half plane one and then back again.
Because it's harder. To put it simply, it really is the upper half plane really brings things into focus. And in addition, so that's reason number 1. And reason number 2 is that I'm going to be interested in the upper half plane anyway. And yeah, so this is something that I only learned, but it's a theorem from 1951 of Morris Heinz. But I was very proud that I discovered it. So it was a nice feeling anyway, for while it lasted. But we posted the paper, and then somebody kindly pointed out to us that this is really not quite as original as 7 years behind it. Yes. Well, anyway. So if you have a function from the upper half plane to itself, analytic, and not the identity map, this is an important point here. There are 2 alternatives. Alternative number 1 is that phi has a fixed point. Let's call it zeta phi in the unit disk, and we call that fixed point zeta. Yeah. It's unique by the Schwartz inequality. It's a unique fixed point, right? So if you have a function from the disk to itself that fixes 0 and 1 more point, then Schwartz tells you that's the identity function. And this is basically the same situation here. Conformally speaking, it's the same situation. So this is number one. And the second one is that there's no fixed point. And in this case, there exists an attracting fixed point zeta phi and the real line, or perhaps infinity. Yeah? That's the we distinguished, unfortunately, at this point, that the upper half plane distinguished this point with infinity, and this is also a unique point as we noticed earlier. Yeah, so for each function that's an analytic function from the upper half plane to itself, there exists, except for the identity function, there exists this unique fixed or fixed point. So either plane fixed or kind of a so this is the theorem. This is the Heinz theorem. Suppose that phi and phi are analytic functions from the upper half plane to itself, and they converge. Phi n converges to phi, and phi is not the identity function on the upper half plane, and therefore phi n itself is not the identity function for n large. Then this point zeta phi n converges to zeta phi. So yeah. If I had known this a little earlier, things would have been different.
Are you missing the hypothesis? There's something phi n converges to phi n. Are you missing pointwise? Okay.
That's recommended by the missing cost.
It's not.
You didn't put the convergence.
But I said it. Yeah. Didn't I say it? I think I did say it. Phi n converges to phi pointwise. Yeah. Thank you. I'll have to correct that particular. And zeta phi n converges to zeta. So that's Heinz's theorem. Yeah. Okay. Suppose that zeta phi n converges to some point C, which is going to be a point in the closure of the upper half plane in the Riemann sphere. Why can we suppose this? So this is another exercise for you. Where it's enough to, so it's enough really to show that Xi is equal to zeta phi. If Xi is a point inside in the interior, then it's going to be a fixed point for the function phi, just because you have uniform convergence of phi n to phi in a neighborhood of the point Xi, right? So that's a pretty trivial. It's fixed without quotation marks. It's just a plain fixed point. If Xi is not in the open half plane, then you throw it to infinity conformally. Yeah, so you just trade it for the point at infinity by changing the functions phi and by conjugating phi and with a fractional linear transformation, and you reduce to the case when Xi is equal to infinity, and in this case the reasoning in the Julia character theorem applies. With a little bit of modification, right? So, with beta equals 1, of course. So that's that. Okay. So that was my function theory interlude for today. 3 proofs. So again, the proof is short like that. We organized a little bit the previous results. But, now, so let's talk about subordination functions. So suppose that we have 2 measures, mu1 and mu2, probability measures on the real line, and denote by mu their free additive convolution. And most of the results that I'm going to talk about refer to the situation in which mu1 and mu2 are non-degenerate measures. In other words, they're not point masses. They're not direct measures. Why do we exclude that particular case? Well, because convolution with the point mass is very easy to calculate. If the point mass is at 0, then that doesn't change the other measure in any way, right? If it's a point, then it's a translation basically. So it's now the Cauchy transform G mu and G mu J, G mu 1, G mu 2 have inverses defined in some angles at infinity. And that's defined by omega G to G mu J inverse composed with G mu. This is going to be somewhere. Yeah. There's some open set where this function actually, an open angle that's now let's recall the additivity of the R transform. So that tells you G mu inverse of Z is equal to G mu 1 inverse of Z plus G mu 2 inverse of Z minus 1 over Z, right? So that's equivalent to the equation that tells you that the R transform is additive. And let's substitute in this, let's substitute the G mu of Z for Z, okay? Well, you get a somewhat different equation. You get, so if Z is replaced by G mu of Z, you get Z on the left-hand side. Then on the right-hand side, you get omega 1 of Z plus omega 2 of Z plus, rather minus 1 over G mu of Z, which is, of course, our friend, the reciprocal Cauchy transform, minus F mu of Z. Yes. But of course, this happens somewhere far away. And now there exists this theorem. We incorporate here results of Belinsky and so on and so forth. But I must emphasize that this perfected form of the theorem is only a few weeks old. So the result is the following. There exist continuous functions omega 1 and omega 2. And I say it later. Omega 1 and omega 2 defined on the upper half plane with values in the closure of the upper half plane in the Riemann sphere, right? So possibly infinite every now and then, such that omega j maps the upper half plane into itself. Omega j restricted to the upper half plane is analytic.
Well, why are you restricting it? It's only so undefined on.
It should be the domain should be the same as the range. Yeah. So correction here, omega j is defined on H union the real line.
Okay. So when you say it's analytic, is it analytic with values in the upper half plane? Yeah, that's okay. But it's extent continuous.
So you should have just put bars on everything.
Actually, I should have put bar on the left-hand side, because the bar is commonly understood to be the closure in the complex plane. But the values are in the closure. So you have two closures here. You have the closure in the upper, in the complex plane, which is H bar, H union R, but the values are allowed to be infinity every now and then. Okay. So again, my apologies. Obviously, it's been very sloppy writing here. But yes, so omega j is analytic on the disk, and that equation that we had, that z is equal to omega 1 plus omega 2 minus f mu, is actually true on the entire upper half plane. Yes. It's the fact that it extends, in all cases, it extends continuously to the real line. So Belinsky had particular cases of this. For instance, if your measure mu has, if one of the measures mu has, he needed a gap in the support of the measure. So let's say, for instance, the measures are compactly supported, and she knew that. And also, if there's a gap in in the supports of one of the measures. So there was a technical point.
But you know, anything like existence of moments, anything.
Nothing at all.
Right, so
No.
that's,
So this for complete yes.
Worried, so it says, your equation in the middle says Z is omega 1 plus omega 2 minus F mu. But in the theorem, it's F mu of omega J.
Yeah, I put F mu on the other side. You see, so you have a Z.
E on this side.
Yeah.
Right, but like, that would say F mu of Z is omega 1 of Z. F mu of omega J is. J of omega J.
Two.
Oh, okay, sorry, yeah.
I wrote it like that. Actually, I would have liked to. I mean, just like everybody is. I mean, we're all lazy preachers, including me, and and I don't like, for instance, to type \box plus too many times. So that's why I use the notation mu. But here I forgot. But by the bottom of the page, I forgot that that I had. Yeah.
That equation.
I'm sorry?
When C is equal to infinity on that bottom equation, is there some, it makes sense to where you check that,
Well,
right?
infinity, well, you can put the Z on the left-hand side. And then you get infinity equals infinity, if you like. That's.
F at infinity is infinity.
Yes, F infinity. And the omega J infinity is infinity as well. So if you want.
Two infinity minus one infinity is.
Right. So they are infinities of the same order. So F of Z is of the order of Z, omega J of Z is of the order of Z. So it all rhymes that way. Yeah.
To infinity and beyond.
So for that one, I mean, so that's so F equals to so F mu 1 omega 2, right? And E equals F mu 2 omega 1. This should be how different it is.
I think no, I think my notation is consistent. Yeah. I think.
One might have different conventions about which one is omega 1 and which one is omega 2. So maybe someone else reverses the label.
Sometimes you see people denoting them omega mu 1 and omega mu 2, but the truth of the matter is that they depend on both mu 1 and mu 2, right? So if you wanted a complete notation, maybe one of them should be omega subscript mu 1 mu 2, and the other one should be omega mu 2 mu 1. Not so attractive.
Kind of read on it.
But let me get to my fourth proof here, okay? Because it's time to prove it. Yeah. So for simplicity, let's denote by big Hj of Z, the function Fj of Z minus Z. Okay. And supposing the problem solved, as we said in elementary school, I noticed that omega 1 of Z is Z plus F mu of Z minus omega 2 of Z. Here I remembered again not to put the box plus. So mu is the convolution of mu on 2, right? So omega 1 of Z is Z plus F mu of Z. But this, of course, is supposed to be Z plus F mu 2 of omega 2 of Z minus omega 2 of Z, which is the same as Z plus H2 of omega 2 of Z. So omega 1 of Z is Z plus H2 of omega 2 of Z. So this gives me a formula for omega 1 in terms of omega 2. Repeat this operation. You get that omega 1 of Z is in fact Z plus H2 of Z plus H1 of omega 1 of Z. So little algebra here. But what this means is that omega 1 of Z is the fixed point of a certain map. Omega 1 of Z is the fixed point of the map that takes of the map which I denote phi Z of W. W goes to phi z of W, where phi z of W is Z plus H2 of Z plus H1 of W. And this is an analytic map from the upper half plane to itself. Therefore, it has a fixed point, unique fixed point. So this tells you another observation here is the fact that phi z is in fact defined for every Z in the upper half plane and in the real lines. And in addition, phi z depends continuously on Z. Okay. So what's the conclusion is that I just said omega 1 of Z is equal to lambda, that's special fixed point of the Z, and apply the Heinz theorem to obtain the continuity of this function. Analyticity is easy. And omega 2 is constructed similarly.
H on real line. So I mean, to define,
You don't need to. Because you see, so you just look at the expression. H2 is applied to Z plus H1 of W. Okay, W is in the upper half plane, and H1 maps the upper half plane to the upper half plane.
so it always looks it up.
Yeah. So where the proof fails in the case that that one of the measures is point mass, is that in that case H1 is a real constant. So that's what that assumption does for you in this particular situation. Okay.
Is there some way that this definition of somehow obvious? I mean, it seems like, I don't know, just for you do a lot of playing around, trial and error expressions. And the fact that there is one that works seems to be a bit of a miracle.
Well, it's once you remember that this is the way it works, you don't have to think about it very much. I mean, you just
And what we do.
then you think some more, and perhaps you come up with something, but perhaps something different. Okay, so that's what the result is. And an exercise for you: find a flaw in the argument above. You see, Jamie found one, but it was not a flaw.
I can find a flawed argument that you're assuming that the measures are given use to non-generous assumption.
Well, that was just addressing that masses have been excluded. However, there is a flaw in this argument which requires a little bit of additional calculation, which Sherban did many years ago.
This is something about this, the fixed point has to be in plane. Because we don't put fixed point on the bottom.
When you have to draw it up, I'm not going to say. I'll tell you afterwards privately, but I want to leave people the pleasure of finding the mistake. I think it's more instructive that way. Does this result fail completely for degenerate measures? Yeah, does it? That's on the basis. So we saw that it fails in one way, in the sense that the measure the maps phi sub z might not be defined anymore, right? But is it a complete failure? Is it a disaster or not? Maybe I should comment on this a little bit because I started with Voiculescu. Voiculescu, so the way that Voiculescu went about this is said, well, have this function omega 1, which is defined. Well, he worked with compactly supported measures at the time. Said, well, you have a function which is defined at infinity. It's a germ of an analytic function. It's infinity, and well, what do? You want to extend it? Experimentally, one would observe that this kind of thing does hold, in fact, and it also seemed to be desirable. And he proceeded to do analytic continuation. Well, how do you analytic continuation? Well, use this monodromy, right? You have to And there's some problems when you do that. You encounter some points where, so there are some points that he had to take care of, and he just made an assumption, a genericity assumption that those some pleasant points don't exist. So in other words, he had a generic result, but of course this is only for the analytic part of the function, the part in the upper half plane. And then Bian eventually came up with the complete proof. But the truth of the matter is that Voiculescu's argument does in fact work even in case where monodromy fails. I mean, apparently fails, but in fact doesn't fail. So yes, but the first published proof of the analytic part of the result is in work of Bian. And the continuous extension of the function to the real line first came up in work of Belinsky and myself in the case when the measures mu1 and mu2 are identical, for instance, or when you take a semi-group of measures in the style of Andu and Roland. Then again, the subordination function extends continuously to the real line, possibly with infinite values every here and there. And that has consequences about that. And I'm going to write the very first consequences in the case of different measures. So let me write yeah, okay. So first consequence was obtained by Voiculescu in that very same paper, in which he proves the existence of omegas in special cases. And the consequence is that mu1 is absolutely continuous and its density is in LP on the real line. Then the same thing is true for mu1 convolved with mu2. So the existence of a density which is integrable to some power follows from the is inherited by free convolution. And this is a result of a very classical nature, because the first time that results like this appeared were actually in work of Littlewood on the disk, subordination on the disk. But he was developing the theory of Hardy spaces. One should call them perhaps the Hardy-Littlewood spaces. So he was working on the theory of Hardy spaces. So his theorem was that if you take a function which is in the Hardy space, some Hardy space of the disk, and you compose it with a self-map of the unit disk that fixes the origin, then the resulting function is also in the same Hardy space, and it has norm less than or equal to the original function. So it was not entirely. So I think this is why Voiculescu looked into this kind of thing, because he was well aware that subordination has this kind of consequence. Yes.
So for the second statement, are you still assuming that the optical density is an LP? Are these two separate statements, or is there the density being an LP of global assumption?
I didn't understand the question.
The last part, is it still assuming LP or just the independent statement? That's an independent statement. Yeah.
I didn't get to that. So yeah, so if the density is continuous, then so is the density of yes, yeah, that's right. So if you have a continuous density, then you also have a continuous density for the convolution. And interestingly, did I say this? Yes, I wrote it here. Differentiability is not preserved. That's perhaps an interesting point. So you cannot hope to get this to. And the reason for this is that if you take a measure with compact support and convolve it with itself a sufficient number of times, you get something which is almost like a semicircle. So even if your initial function was a C infinity function, you convolve it with itself sufficiently many points. Yes, yes. That corner emerges at some point. That corner emerges. So you might have differentiability for a while, but not forever. So what else? This is something that I observed a little bit later. It's a description of the point masses of a free convolution. So is a point mass of the free convolution of mu1 and mu2, if and only if that point can be written as T1 plus T2, where the mu1 of the point T1 and mu2 of the point T2 add up to more than one, strictly more than one. So as you see right away from here, that the free convolution has only finitely many, of course, if both of them are non-degenerate measures here, right? So if one of them is degenerate, the other one can have any number of atoms, and you translate that, you still get infinitely many atoms. But if they are non-degenerate, this equation, this inequality has only finitely many solutions. So it's only finitely many atoms, and I think it is time for me to stop. Mark, almost on time.
So this subordination map, omega-1 and omega-2, they map the sort of extended upper half plane continuously to itself. Can you say anything about how close to being surjective it is? Like how much of the upper half plane is omitted by the range of omega-1? It won't in general map the upper half plane onto the upper half plane. It's leave out. You know, just simple examples will show it omits something. And can you say, like, what is the omitted domain in the upper half plane? Any
You omitted.
well, okay.
In specific case, you might say that something is omitted, but in general, the omega-1 could be a surjective map.
Okay, but can you say anything about what the image of omega-1 is?
Well, that's the general statement that I'm making, that omega-1 of the upper half plane is contained in the upper half plane. That's the most general, that's the most precise, absolutely general statement. So yeah, that's a problem. That is a little difficult. So for instance, if you when you work with let's say when one of the sum ends is an infinitely divisible measure, then one understands a little better what the range of omega-1 is, and it's related somehow with so it's the upper half plane minus some bubbles around the support of the yes, yeah. So that happens in that case, but in general, that's not the case. In general, omega-1 and omega-2 could both be onto the entire upper half plane. It's a bit unfortunate. They're not injective in general. Yes.
This LP result, does this include P equals infinity? So is the suit norm of the densities decreasing?
Finite for sure, because that's how the Littlewood result works for P, but for P infinity is Littlewood is also true for P infinity, but I'm not sure on the upper half plane things might. I'll have to think about it a little bit. Yeah, no. Yeah, I suppose he's right. There. He's answered your question. Yes.
What if while you want at the quality alpha stable also, so if that including applies to the
No. It's like Brownian motion. If you start from somewhere else, you don't start from zero. Brownian motion is not going to be infinitely divisible, generally speaking.
Sufficient condition.
The decay. You want the decay. The decay is probably kept. I cannot. But in fact, one expects when you convolve with a very nice measure, you'd expect it to improve a little bit. You know, in a classical case, you pretty much say that's pretty much the same thing, because you just have translates of the things and you add them up. But in the free case, there's some kind of concentration that happens, this is something that I have never been able to quantify. So this is in fact I will ask a question a little bit later. It's yeah. So there's a question that you want me to stop? Yeah. So it's, there's a question that, so this is for the classical probability. So there's an operation of symmetrization. I mean, when you study limit theorems at the beginning, you look at something like this. You have, look at the difference, x minus y of two identically distributed variables, independent identically distributed variables, and that's a symmetrization. And then there are results that that connect the tails of a symmetrization with the tails of the original measures, if you make them somewhat centered. So is such a result true for free symmetrization? I cannot answer it yet. I've asked all of my students. I asked Ping, he didn't do it yet. So so that's a question that I think it's maybe it's not of great theoretical importance, because the result that one can derive from have been obtained one way or another in different ways, but it's a question of principle, which I think is of some importance.
So this time,